Okay, I see that we're live on YouTube. Welcome everyone. Okay, see we are two people watching, one of them being me, so we'll wait a bit more for more people to join us. Feel free to drop a message in the chat if you want, either on YouTube or on the live chat topic on our Telegram group. Yeah. Let me just remove this. Perfect. All right. Hi, Lunes. Welcome. Oh, we have 4 people now. Great. So just as a reminder, if you are commenting on Rumble, because we are live on Rumble too, I can't read the comments during the live because Rumble is not available in France due to some funny regulatory business. And I don't want to use a VPN while live streaming because I'm afraid it would create some networking issues maybe, or add some additional latency. So that's why I can't see the live Rumble chat because I'm based in France, and so I can't access the Rumble website without a VPN. And I don't really want to try live streaming with a VPN. It could work, I guess, but yeah, let's not tempt the devil. So you have the Telegram live chat available if you don't want to use YouTube, which I can understand. So yeah, speaking of the Telegram live chat, while we wait for potential other people to join us, just a quick reminder of what the Plan B Labs Lightning is. Basically, it's both a Telegram group, a Telegram community, which you can join by scanning the QR code here. And one of the things we organize in this community is this kind of bi-weekly live sessions where the goal is to discuss recent news, new developments in the Lightning ecosystem. The goal can also be to try to create projects inside our little community to do practical exercises, for example, in order to better understand how Lightning works through real examples or by writing a bit of code and stuff like that. So a lot of the time it will be technical topics, sometimes quite advanced, but I always try to be as inclusive as possible. So even if you don't have, if you think you don't have a lot of knowledge about Lightning, you should still be able to follow us. And if there is something you don't understand, feel free to ask a question, of course. That's why the chat is here. And you can also join me on stage. I can easily give you a link so that you can join me in the video if you want to have some higher bandwidth communication. That can be great, for example, if I say something that isn't exactly right, or if you have a question and something that you would like to better understand. And you can, of course, come without showing your face if that's something that you don't want to do. It's possible as well. And so what are we going to discuss today? Today, there are 3 main topics that I curated from the last 2 weeks. So the biggest one, let's say, in terms of how much time I plan to spend on this today, is Spark going mainnet. So we'll cover what Spark is exactly, basically, and so the fact that recently announced, so I think it was last week or maybe the week before, that they were going mainnet. So they were basically launching the real version of Spark and not just test versions anymore. Then we'll have a little chat about channel depletion because there was some interesting post by René Picard on the Delving Bitcoin forum, which is basically now the now that there, so since a few months there isn't any Lightning Dev mailing list anymore because all mailing lists that were on Linux websites were closed down. And so for the Bitcoin Dev mailing list, it was migrated to Google Groups. And for the Lightning Dev mailing list, it was basically migrated to Delving Bitcoin, which is a forum where technical discussions happen around Bitcoin. So there is a tag system to specify if the conversation is around Bitcoin, around Lightning, around protocol, around application development, and stuff like that. So we'll take a look at that. We will, of course, explain the context of what channel depletion is and what is kind of the state of the research right now, as well as delve into René Picard's recent post. And then we'll take a look at at multi-node Lightning payments in Cashew. So what we can call multi-node because it's a marketing term that the Cashew people use. Because there was a few days ago probably the first real life Cashew to Lightning transactions that involve multiple Lightning nodes in one single payment. And we'll see why I think, and a lot of other people, of course, that it is quite a huge deal. So yes, that's it. That's the program for today. Feel free to ask any question or add any remarks that you may have. So I see we are 7 people now, so that's great. Maybe we will break our record. So Spark going mainnet. So the Spark team recently announced the launch of Spark on mainnet. So here, if you follow this QR code, you can see the announcement. I'm going to. I can do that easily. All right. Maybe I can do it this way. Yeah. All right. Oh no, actually, it doesn't work. All right. Let me just. Okay. You know what? I'll show you that later. Sorry about that. Let's go back to the slideshow. I wanted to show you the web page where they did the announcement, but actually it's not that important. They're just basically saying that, sorry, they launched on mainnet, and that basically it's not ready for production yet, not at all. And so basically the idea is to open it to more developers so that people can try the protocol, start playing with this. There are a few SDKs, so development kits, which are available for developers who want to try to build some little apps using Spark right now. Hi, Turbo Exchange, welcome. And so before we go into all of that, we must first see what Spark is anyway, because it's quite a new protocol, I think, and maybe it didn't make a lot of the news. Even recently with the mainnet announcement, I'm not sure that everybody in the Bitcoin ecosystem at large has Spark on their radar yet. And so Spark is, so it was a project that was kind of incubated inside LightSpark. And so LightSpark is a Lightning company which was launched by David Marcus. So which were working at, David Marcus was working at Meta previously, worked on the Libra project and all that. And he had an epiphany doing all this crypto stuff and realized that Bitcoin is what matters. And so we came back with LightSpark, which is a Lightning infrastructure company It's often compared to voltage, although both companies have and both products have different trade-offs. But it's quite kind of the same kind of idea, which is basically to have managed nodes, managed Lightning nodes in the cloud, so that you, at a company who want to integrate Lightning or receive Lightning payments, you don't have to really spend too much time on the payment infrastructure part, and you can focus more on your product. And so basically, the Lightspark inside Lightspark, they realized that they were hitting a lot of walls when it comes to scalability and stuff like that using Lightning, because that's one of the kind of difficult aspects of Lightning, is that if you want to use Lightning, you have to have a channel, and so you need to have a payment channel between two parties. And so quickly, when you want to scale things, if you want to remain self-custodial, you would need to have one channel with each of your customers, and that's where things tend to become a bit hard to do. And so that's why they tried to take a look at other solutions that could combine with Lightning in order to keep the self-custodial aspect as much as possible, but while making maybe different trade-offs that would allow for better scalability in the context of multiple users interacting with one main entity. And so that's why they took a look at state chains. And so state chains are not really an entirely new concept. So state chains are actually quite old. So of course, in Bitcoin, everything is always quite old. It just depends on how far away you come back. But I will cover in a few moments what a state chain is exactly. But in the Spark context, the state chain has a few interesting um, capabilities. One of them is that there is a quorum of operators working inside the same entity. So we'll see in a minute what this means. It has Lightning capabilities. So even if it's a state chain protocol, you can send and receive via Lightning. You can break coins into smaller denominations. So maybe this kind of phrasing will remind you of things like Cashew or Arc. And it's something that isn't necessarily easy to do in a state chain context. So we'll see about that. And it has shitcoin support. So of course, I say that with a grain of salt, but basically it has a lot of, it has basically two big modules in Spark. One of them, which is the state chain aspect, the wallet aspect, and the other one, which is basically the token issuance aspect, which we will not really talk about this token part today. But yeah, just know that it exists. And one of the main market that the Spark team seems to be aiming for with this token issuance is basically stablecoins, which makes a lot of sense because Spark seems to be really a payment solution. And so the only tokens that are really interesting in a payment context are stablecoins. And of course, Bitcoin, but I don't really count Bitcoin as a token of itself. And despite what the name might suggest, it's not another Arc implementation. So yeah, Spark, it has some aspect that make it resemble a bit Arc, but it's not really another Arc implementation. And so what is a state chain? Sorry about that. This little blue guy shouldn't be here. So a state chain basically is a way to send a coin off chain. So basically you have a construct where you can exchange a coin without having to make an on-chain Bitcoin transaction. And how does this work? So you have Alice, our good old Alice, which comes to a state chain server. So here the state chain server is represented by this little cute cat. So once again, this blue guy here, just something I forgot to remove, but it shouldn't be here. And so what Alice and the state chain server do is that they communicate and they create a shared key by combining their own keys. So each of them have their own public private key pair, and they combine them in order to create a shared key that is the aggregate of both keys. But what they share are only, of course, their public keys. So they don't share their private keys, they only share their public keys. But since Taproot and Schnorr signatures, we have something very cool, which is that we have some linearity when it comes to key composition. And so if you sum two public keys, then the private key of the sum of the two public keys is the sum of the private keys. So that's really awesome because it means that if Alice and Mr. Cat, so our state chain server, aggregate their keys in order to create another public key, then the private key that spans from this public key will also be the aggregate of Alice's private key and Mr. Cat's private key. Hi, Alphonse, welcome. And so that's a great thing to have, a great property. And so once they have created this public key, Alice creates and signs a transaction that spans from coins that are on her wallet and creates a new output on this public key. So basically, she funds the public key, she deposits funds into this address, but she doesn't broadcast this transaction yet. So it must remind you a bit of how we fund the Lightning channels, because it's basically the same flow of creating a funding transaction, signing the funding transaction, but not broadcasting it right away. Because what we want to do before Alice broadcasts the funding transaction is she wants to first have a pre-signed exit transaction in order to be able to do a unilateral exit. For example, if Mr. Cat here stops responding. So it's really similar to Lightning in that regard. And so what Alice and Mr. Cat do before Alice publishes the transaction is that they co-sign, so they each using their own private key, so their own half of the private key of the aggregate key. They co-sign two exit transactions. So actually, what I mean by that is that the exit transaction takes the exit process, the unilateral exit process takes two transactions. And so they sign both of those transactions, which we will see in more details in a few seconds, which spends the funds from this output that Alice is creating with the funding transaction. And once these exit transactions are signed, Alice can safely broadcast the funding transaction because now she has everything she needs in order to be sure that she can exit the state chain in a unilateral manner. So she doesn't require the participation, the involvement of Mr. Cat anymore. And so it's great because it means that even if Mr. Cat has a connection issue or anything like that, she will be able to get her funds back on chain in the worst case scenario. And so the exit transactions, so there are two of them, as I said. There is one transaction that is called a branch transaction in the context of Spark. So it's a I will be using the Spark terminology sometime in different state chain protocols. It's not really the same words that are used, but it's usually the same concept. And so this branch transaction, what it does is that it takes the state coin output, so basically the output that was created by Alice's funding transaction, which is on the address that corresponds to the aggregate public key between Alice and Mr. Cat. And this branch transaction, what it does is that it spends this output and it creates a new output that is encumbered by a relative time lock. So basically, this new output can be spent by Alice, but Alice has to wait for a number of blocks after this branch transaction has been confirmed before she can publish, she can spend from this output here with a second transaction. And this second transaction is is the actual exit transaction, which spends from the time locked output right into Alice's address. So it can be whatever address that Alice specified during the step 3 here. And so this time locked output is quite important, and we will see right away why it's important. But so just to reiterate and to be sure it's clear, it's a bit like it's quite like actually unilateral exit in the Lightning context. It's a 2 steps exit, and so first we take the output that is in the state chain, we spend it, so we can spend it right away in order to create a time locked output, and so this is a relative time lock. So as soon as the branch transaction confirms, this time lock starts to tick. And so, for example, if the time lock is 30 blocks, then 30 blocks after the branch transaction confirmed, Alice will be able to publish the exit transaction that spends from the time locked output right into her wallet. And this way she can recover her funds on chain, even if Mr. Cat stops responding, because she pre-signed these transactions with Mr. Cat's help. And now, so it's great. We saw that we can create a shared public key and we can deposit funds on this shared public key. But what's the purpose of this? And so the idea is that is to be able to then do an off-chain transaction in order to transfer the funds that are on this public key from Alice to another user of the state chain. So, for example, Bob, which is what we see here. And so how does this transfer occurs? So let's say that Bob wants to receive from Alice. So what will happen is that Bob will first send his public key to Mr. Cat. Mr. Cat then will tweak its own public key so that the aggregate, so let's say the sum of Bob's public key and Mr. Cat's public key, new public key, is equal to the funding public key that Alice and Mr. Cat created in the previous slide. So basically, the sum of Alice public key plus Mr. Cat public key number 1 is equal to Bob public key plus Mr. Cat public key number 2. So basically, Mr. Cat tweaks their public key in order so that the aggregate is still equal to the same public key. Then Bob and Mr. Cat, they co-sign a new pair of exit transactions. So this way, Bob can be sure to be able to do a unilateral exit if he wants to. And then Mr. Cat deletes their previous key, so the one they used in order to create the aggregate key with Alice. And so what this means is that now that Mr. Cat deleted their previous key, Alice can't ask them to collaborate in order to sign a transaction that spends from the state coin, which is on the public, the aggregate public key. So Mr. Cat can't collaborate with Alice to sign transactions from this public key anymore because it just deleted the key that would let it do so. And so the only way for Alice to get the funds would be with the unilateral exit path, where she needs to wait for the expiration of the relative time lock, as we saw. And so what we want here is we want to transfer the funds to Bob. And so we already saw that since Mr. Cat deleted their previous key pair, they can't do any collaborative transaction with Alice in order to spend the funds that are on the state coin output. And so now, in a collaborative manner, only Bob can can ask Mr. Cat to do such a collaborative transaction. But the unilateral exit path remains, in which Alice could just do her branch transaction, wait for the time lock to expire, and then sweep the funds to her own wallet in the exit transaction. But in order to ensure that Alice can't use this path either, what we do is that in Bob's branch transaction, which he just co-signed with Mr. Cat, in this branch transaction, the time lock that encumbered the output of the transaction is selected so that it is strictly less than the time lock that encumbers the time locked output of Alice in her own branch transaction, which means that even if Alice was to try to get the funds on chain using her branch transaction, then Bob could publish his own branch transaction, and the time lock on Bob's branch transaction would expire before the time lock on Alice's branch transaction. And so Bob would be able to publish his exit transaction before Alice, and Bob would be able to claim the funds this way before Alice. And so that's how we ensure that we effectively transferred the property of the funds from Alice to Bob. So and we did it all off-chain because we only need to publish these transactions if we need to do a unilateral exit. But as long as we don't want to exit the state chain, we can just have Mr. Cat tweak his public key in order to combine it with the public key of the new owner of the state coin, and deleting the previous key material in order to ensure that the state coins, so basically the funds that were deposited in the in Alice's funding public key, so in the public key that Alice's computed with Mr. Cat in the beginning. So the funds don't move on chain, but the ownership of the funds is transferred off chain, as long, of course, as Mr. Cat is honest and really deletes the previous keys, because else Mr. Cat could, for example, not delete their keys if they were a bad actor, and, for example, collude with Alice in order to collaboratively sign a transaction and then steal the funds from Bob. So it's really it's kind of self-custodial, but it's not as self-custodial as trust minimized as Lightning, for example, because in the context of a state chain, generally, you need to trust the state chain server not to collude with other users. So yeah, that's basically how state chains work. I hope it's clear enough so far. Feel free to ask any questions if something is not really spot on. And yeah, maybe it reminds you of another protocol which was called Mercury. And so actually, maybe I will share with you the Mercury protocol, because I think it's quite interesting. Let me just quickly change share screen again. Hello. Yep. All right. So here you have the website of Mercury Layer. You have the overview here. So I can just quickly copy paste the link in the live chat channel. There you go. And so basically it uses a state chain protocol as well, but it's not exactly the same. So here, if you take a look at the animation, you can kind of get the most of the concepts that we just explained. But yeah, what are some key differences between Mercury and Spark. So if you want, you can see Mercury as a virtual open dime system. So for those who don't know, an open dime, it's probably a trademark, so that's why I put the TM. It's a device that is manufactured by ConKite, and basically it's a USB stick, and you can, when you plug the USB stick on a computer, you can see the public address of the public Bitcoin address that is saved inside the USB stick. You can deposit to the USB stick, but in order to spend funds from the USB stick, you need to crack a seal on the USB stick. And so it's very easy to see when an open dime has been opened and when someone has revealed the private key. And so this can be used to an open dime can be used to move Bitcoin around, literally physically. So you deposit funds on the open dime, you give the open dime to someone, they can check by plugging the open dime into their computer how much funds are on the open dime, and they can, by inspecting the open dime, they can check that you didn't crack the seal, and so that the private key is still concealed, hasn't been revealed yet. And so this way you can move Bitcoins physically an arbitrary number of time. And so the Bitcoin on the blockchain, they stay on the same address, but they change, the ownership of the Bitcoin changes depending on who has the open dime, the USB stick at a given point in time. And so basically what Mercury is a virtual open dime where you can deposit funds into the state chain, and then you can just transfer the ownership of the whole coin to another user of the state chain. And so the funds didn't move on chain, but someone else now is able to spend them by co-signing the transaction with the state chain server, or by doing a unilateral exit if required. And in Mercury, there is a blind signing, so a bit like in eCash, which means that the state chain operator doesn't know what are the transfers that are happening. So basically, who sends money to who, which is as well a great in order to reduce the chances, that the server colludes with another user in order to steal funds from you, since the state chain server is blindly signing. They can't really be sure of what is going on in the transaction, and so it's harder for them to be able to collude with a specific user in order to steal funds from another user. They would have to steal funds from everyone in order to be able to steal funds, basically. So that's Mercury. Really, the idea is to have an off-chain mechanism in order to which enables off-chain private transfers of Bitcoin in a virtual manner. So really, it's a virtual open dime. And Spark is a bit different. Spark is basically what happens when a state chain has a baby with an arc. So it's really focused on payment, off-chain payment at scale. And so really, it's not really the same use cases. And so it has a different set of trade-offs, of course. And so here is a table with a few of the key differences between Mercury and Spark. And so as I said, in Mercury, you have only one operator, one Mr. Cat. So voilà, here, only one Mr. Cat. Whereas on Spark, you can have multiple operators, multiple computers that can sign transactions, and that are grouped in a single entity. So it's the same Spark server, but with multiple signers. So multiple Mr. Cat here, and it takes so you can define a threshold that is required for signing transactions. And so basically in Spark, this threshold determines, it's a bit of a trade-off between security, safety, and liveness. Because let's say you have 5 Mr. Cats in your Spark server. So uh, you can call them guardians in the context of Fedimin, for example. So five signers, 5 operators. If your threshold is that only one operator is required in order to sign transactions, then it means that it only takes uh, compromising one operator to be able to, for example, collude for this operator to be able to collude with one user and steal funds from another user, for example. But on the other hand, you have very good liveness because up to 4 operators can go offline, and the fifth operator can still sign transactions with users on its own. It doesn't need the 4 other operators. On the other hand, if you decide that you require 5 operators to sign every transaction, to co-sign every transaction, then it's way harder for operators to collude because it would require the 5 of them to agree to try to defraud users. But on the other hand, you have good security, let's say, if we admit that, so you have better security, let's say, than on the previous example. But now you have your liveness isn't as good because it only takes one operator to go offline, and then the whole Spark server is not usable anymore because you decided that your threshold is 5 of 5. And so, of course, probably the good trade-off is somewhere between 1 of n and n of n. It's a bit like multi-signature and stuff like that. But it's interesting that you can define the quorum and configure it on a server basis. So basically, if you have one Spark server and another Spark server, they can decide on different trade-offs and so have different quorum rules in place. But so that's one big difference between the two. And now, as a reminder, in Mercury, you have blind signing, which is the last row here, which helps a bit alleviate the fact that you have only one operator. Whereas on Spark's end, you don't have blind signing, which means that the Spark entities, so the Spark operators, they see the transactions that happen. They know which user sends to which user. So that's not really, that must not be seen as a privacy layer, for example, because it's really not that. It's really a payment, an off-chain payment layer for scalability, and it doesn't really have huge privacy benefits. So it has the privacy benefits of being off-chain, but the Spark operators see what you're doing. So they did this because so the reasons behind this choice are, for example, that it enables the Spark operator to keep a copy of the transactions, the pre-signed transactions on behalf of the users. So, for example, the users don't, if they forget the state, so it's not a big deal because the Spark can still give them the transactions back. So they both have unilateral exit, and they do this in a quite similar way with the time locks and all the things that we previously saw. And another key difference is the notion of arbitrary amounts, because as I said, Mercury is really like a virtual open dime, which means that when you deposit, let's say 1 Bitcoin, so you do let's say it's not a Spark, it's a Mercury state chain. You deposit 1 Bitcoin, into the state chain server. So you have what we can call a state coin. And then you can only send the whole state coin, which is held on the aggregate public key. You can only transfer the whole thing, the whole state coin to the new owner. So basically to another user of the state chain. Like you can only, it's similar to how you can only give the whole open dime to someone else, and you cannot, I don't know, split the open dime in two. It's not possible. Whereas on Spark, they use the branch transaction and a whole, let's say, tree and a leaf structure to be able to um, break a state coin into smaller state coins if required, and then they can aggregate eventually these state coins back together if needed. And so this enables arbitrary amounts. So you can basically make send funds of any amounts. It resembles a bit how it's done on Arc or in Cashew, where you can basically melt a token and create new tokens, and then with different values. But the sum of the new tokens is equal to the previous tokens that was used to create them. So that's a key difference as well, and that's really a difference that highlights the different use cases, because really Mercury is this privacy layer, off-chain layer, where you can just shuffle around some UTXO basically between different users off-chain, whereas Spark is really meant for payment at scale, and so you really need to be able to send whatever amount you want. It's not really it wouldn't be a payment system if you can only send one specific amount. It doesn't work at all. So that's why they really went with this innovation of arbitrary amounts. So yeah, maybe you can just take a look at how quickly this splitting. I don't remember what it's here. Maybe so. Yeah. Yeah. So basically, here, if you're interested, they explain how you can. So I'm going to share this in the chat as well. They explain how you can split a leaf. So what they call a leaf is what I call a state coin, basically. And so you end up with a Spark tree where you have your original branch transaction, and then you have the individual leaves. So I'm not going to go into too much details here. You can see it for yourself. If it's interesting, we can. If you find it interesting, we can maybe delve into more details here on a subsequent session. But well, yeah, basically it's one of the big innovations, I think, so big differences between Spark and previous state chain protocols is really this idea that you can split leaves to spend smaller denominations. Yeah, great. And Lightning in all that, because we covered a lot, Spark a lot, and it's always great to see what other layer 2 payment systems exist on top of Lightning and what different trade-offs they make. But Spark also supports sending and receiving via Lightning. So it's really it connects to a lot of things we saw in previous sessions around Lightning being really the bridge between various payment systems. So, for example, we saw a few sessions ago how Arc can use Lightning in order to transfer funds to users that are outside the Arc, or how Cashew mints can use Lightning to transfer funds between mints. And we will see that also today, another example of that. But basically, the flow is that if Alice wants to send, sorry, for example, here it's the receive case. So Alice wants to receive funds from Bob, and Bob is not on the state chain, so she wants to receive via Lightning, for example. But in the end, she will have funds on the state chain. So what Alice does is that she generates a pre-image. So that's something that we are aware of. Quite classic. You start by generating a pre-image, which is a random number, basically. Then you compute the hash of this pre-image. And then Alice sends the hash to what is called the SSP. So basically, it's the state chain service provider. It's like the LSP for Lightning service provider, or ASP for Arc service provider on a Spark state chain, there is the Spark service provider. And so Alice gives the hash to the SSP, and the SSP uses this hash to generate a Lightning invoice, with the destination of the invoice being the SSP's Lightning node. So Alice does the creation of the pre-image, but the creation of the invoice is created by the SSP. Then the SSP gives the invoice to Alice, and of course Alice checks that the invoice is indeed for the hash that she gave to the SSP. If it was a different hash, it means that the SSP would have used their own pre-image and would be able to claim the funds for themselves. So she really needs to check that. Then Alice shards the pre-image using Shamir secret sharing and distributes it to the Spark entity. So basically, the Spark entity is all the Spark operators. So if you have 5 Mr. Cat in our example, it's basically 5 Mr. Cats. So it's all the operators on the quorum. Can be one or more operators. And so Alice shards the pre-image and distributes it to the Spark entity. So that will be used later for the Spark entity to be able to claim together the funds when the Lightning payment arrives. And so, for example, it's not really clearly stated, but my understanding is that if, for example, the threshold of the quorum is that you need 3 Mr. Cat out of 5 in order to sign a transaction, then Alice shards the pre-image with SSS in a way that three operators are required to reconstruct the pre-image. 3 shards, in other words, are sufficient, are enough to reconstruct the pre-image out of 5. And then Alice, once she's done that, Alice shares the invoice to Bob. Bob pays the invoice. So here we are in regular Lightning, how Lightning works. And so the invoice the destination of the invoice is the Spark service provider. So of course the Lightning payment arrives to the Spark service provider. When it arrives, the Spark service provider cannot claim the funds because they don't know the pre-image. They only know the hash of the pre-image, which Alice gave them at step 2. And so then the Spark entity together, they can reconstruct the pre-image because they have shards of the pre-image. And so the Spark service provider makes an API call to the Spark entity, to the Spark operators, to perform an atomic transfer of leaves in exchange for the pre-image. So basically, since on the one hand we have an HTLC, and on the other hand we have an off-chain representation of a UTXO, we can do an atomic swap with a pre-image between them, which is what we use, for example, in order to do atomic swaps between Bitcoin and Lightning, or between Bitcoin and Liquid, or between Liquid and Lightning. So it's always the same idea. If you have something, if you have a UTXO-based coin, you can do an atomic swap using pre-image. And so the Spark service provider initiates the atomic swap, and then the Spark operators together they reconstruct the pre-image using their shards. So for example, if the split was 3 shards are required out of 5, we only need 3 shards to reconstruct the pre-image. And then once they know the pre-image, they can settle the swap, the atomic swap of leaves for the pre-image. So they are getting the funds, and in exchange they give the leaf, sorry, to Alice. And so one of the things that is interesting is that it means a Spark user, so Alice, for example, in our example, can receive funds from Lightning while she's offline. So she would be required still in order to create the pre-image, send it to the SSP, and send shards of the pre-image to the Spark operators. But once those steps are done, she doesn't need to stay around in order to receive the payment, because she really isn't involved in the Lightning part of the payment other than creating the pre-image. And she doesn't have a Lightning node or anything like that. She really relies on the SSP's infrastructure, the SSP's channels. And so she doesn't need to be online to once the pre-image has been generated. And so it's something that you could, for example, also create in advance. You could create the pre-image in advance, and then have some static identifier like a Lightning address, where people can send you a request, and then the SSP or the SC, but it would typically be the SSP, can respond to people who try to pay you on this static identifier by sending one of the hashes that you provided them beforehand. But there is a caveat, which is the same as for Lightning address servers, which is that you cannot be sure that when someone tries to pay you on your Lightning address, the server will respond with a hash that belongs to you. So an invoice that pays you indeed, and will not try to silently take money that was destined, that was meant to reach you, and keep it for them. So it's something, it's really not specific to Spark and to SSP and stuff like that. It's really a broader issue when you are relying on someone else to resolve a payment attempt to you and respond to this payment request with an invoice. If you don't control the server that does this response, you cannot be sure that they will be using invoices that really pay to your pre-image, and not respond with another invoice that pays their own pre-image which they generated. And so they could, this way they could keep the funds for themselves, and you wouldn't even be aware of that unless the person that pays you tells you that they are paying you out of band, and then you could see that they told you that they paid you, but you didn't receive anything, and then you could maybe guess that the SSP or the server in a more generic context tried to steal from you. Actually, not tried, but managed to steal from you. But yeah, if Bob doesn't tell you anything, you wouldn't be aware of that. So yeah, that's how Lightning integrates into Spark. So quite interesting. And of course, you have receive capabilities as well. So if you follow the link here, you can see the Lightning interoperability part. So it's basically here. I just took the schematics from their website as well, and you have receive capabilities as well. And yeah, as I said, all the operations here are atomic under the same one of n or minority of n trust assumptions. So basically, that's what I mentioned with the fact that Alice, when she shards the pre-image, the sharding, the number of shards that are required to reconstruct the pre-image, it corresponds to the threshold of operators that are required more generally inside the state chain, inside the Spark server to sign transactions. It's the same. So basically, what I'm trying to say is that when you transact, when you do a transaction inside the Spark server, so with another user of the same Spark server, or when you transact using Lightning, you have basically the same trust assumptions when it comes to it would require the collusion of 3 operators out of 5 to steal funds. It's the same assumptions, which is a quite nice thing to have, because it really simplifies how users can reason about whether they trust a Spark entity or not, depending on this kind of thresholds. And once again, it's really a compromise between safety and trust minimization on one hand. So if you have if you have a high threshold, so for example, 4 out of 5, you have the trust required is reduced, but then you have um uh, the liveness requirements are also increased. So basically, you really need to have 4 out of 5 operators online in order to process transactions. And so if 2 of them have a failure, then the whole Spark server cannot process transactions anymore. So it's really a compromise, a trade-off between those two factors. I think, yeah, that's it for Spark. I hope it was clear enough. So I dropped some links in the Telegram chat, in the live chat channel, if you want. Feel free to ask any questions if something wasn't clear, if you have any remark. And now maybe we can move to actually before channel depletion, and I think it makes more sense to jump to multi-nut payment, and maybe we'll keep channel depletion for later. So here you have a small demo published by Kale. So for those who don't know, Kale is basically the dev behind Cashew. And so, yeah, maybe we can just take a look at the payments. So basically, you need to send funds to someone. You pay an invoice. You go. And so you do a multi-nut payment. And so here, if I pause, so basically when you're using eCash and Cashew, for example, when you want to send funds from a mint to someone that is not on the same mint, you need to use Lightning in order to reach them. And one of the core ideas behind Cashew is that you can have multiple mints. So basically, you are talking with multiple different servers, and each servers has their own eCash token, which is supposed to be, which is basically an IOU against Bitcoin, against real Bitcoin. And by having multiple mints, you can diversify your risk across multiple mints. Because as a reminder, an eCash mint is a custodian. So you're not sure until you try to withdraw funds and in exchange for real Bitcoin, you're not sure that the eCash token they give you and that should be worth 1 sat per token is really, it's not 1 sat per token, but you're not sure until you try to really get real Bitcoin that the IOU is real. And so the idea is to have multiple mints so that you can spread your risk more evenly. And if one mint rugs, then you only lose what was on this mint, and you don't lose what was on other LC trustworthy mints. But one of the big hurdles with this kind of setup is that if you have on your eCash wallet, you have, let's say you have you have 200,000 sats, but it's split between 4 mints. Let's say it's evenly split. So you have, in total, you have 200,000 sats, and you have 50,000 sats on mint A, 50,000 sats on mint B, 50,000 sats on mint C, 50,000 sats on mint D. Then if you want to pay, let's say, 100,000 sats, you would need to withdraw funds from at least 2 mints and in only one transaction. And so that can prove to be a bit cumbersome, but it's possible to actually spend funds inside a Lightning transaction using multipass payment, which is something that is really standard on Lightning since a few years, to make one Lightning payment of 100,000 sats using 2 different Lightning nodes. And so that's what we are saying here. So the user is trying to pay a 100,000 sats invoice. And as you can see, multi-node payment is selected. And so there are two mints. One mint that runs on Core Lightning. So because of course for each mint you need to have a Lightning gateway. So basically a Lightning node that is connected to this mint, and that lets you withdraw eCash from this mint and transform it into and withdraw it through Lightning basically. And so here you can see that you have 59,000 sats on this mint, which is using a Core Lightning node as a gateway. And here you have 59,000 sats on this other mint, which uses an LND node as a gateway. And so what the video showed is that you can create a transaction, that spends funds from both mints inside the same Lightning transaction, quote unquote the same Lightning transaction, using multi-part payments. So basically the receiving node doesn't care that the payment came into multiple chunks, because it's something that happens anyway. Even if you're sending funds from one single node, the payment will be often split into smaller chunks in order to be able to route it more efficiently across several channels, rather than trying to make the whole payment fit one unique route. Something that is already done at scale automatically by all Lightning implementations is split the payment into smaller chunks and send one chunk along route A, one chunk along route B, and one chunk along route C, for example. And then the receiving node will only accept the chunks if the sum of the chunks is equal to the desired amount. So that's why we call it atomic multipass payment. It's because either all the chunks arrive to the destination and then the payment succeeds, or if some chunks are missing, then even the chunks that arrive to the destination are failed, are considered as not received, basically, and the whole payment fails. And so it's great because basically one of the big assumptions behind the trade-offs of Cashew is that it's fairly easy to spin up a new Cashew mint. And so it is envisioned that in the future there will be many Cashew mints. And so user can really spread their risk across multiple, and we are talking really several mints. And the fact that really this works, and so this is really demonstrated here with a real Bitcoin, a real Lightning transaction, really means that this trade-off can work, and that you can have, so for example, because what I'm trying to say is that one of the big alternatives to Cashew is Fedimint. And so in Fedimint, basically the idea is that instead of having one entity that controls, let me see, basically in a Fedimint, instead of having one entity that is the custodian for the funds of the users of the mint, you have a set of guardians, which is a bit like in the Spark configuration we saw. It takes a majority of guardians to approve a transaction for it to take place. So basically, it's a multi-signature. The funds, instead of being spendable by only one entity, are held in a multi-signature, and it requires a majority of guardians to be able to spend the funds. So which means that a majority of guardians need to collude inside the mint in order to rug pull the users. And so you have this, but the problem is that it requires some kind of consensus engine for the guardians to agree on transactions. And so it really adds some complexity. So that's what we can see here to the process of running a mint. And Cashew, on the other hand, took a different approach with very easy to run mints with only one custodian in each mint. Um, and then users can, since mints are easy to run, there are many mints, many cashew mints, and user can select multiple mints and can spread their funds across those mints. And now that we have this kind of multi-node payments working, so it's kind of old because already in January there was some demonstration of that, but I think it's the first one on mainnet. Um, then you have the same UX for multi-mint cashew to Lightning as what you have for one mint, one Fedi mint to Lightning. And so now you can just decide what's your preferred trade-off and trust model between splitting your funds across multiple mints, multiple small cashew mints, which means that it only takes if it's easier for one mint to rug pull, but then you only lose what is on this specific mint. And on the other hand, the other set of trade-off is in the case of Fedi Mint, it's really harder for the mint to rug pull because it would take, for example, three different entities to collude in order to rug pull. But then on the other hand, you have all your funds inside the same mint, and then if this threshold is reached and three of the guardians collude, then you lose everything. So it's really a different set of trade-offs, and you can of course combine trade-offs. You can imagine having some funds on cashew mint and some funds on Fedi mints. But now that you can have really the same user experience when it comes to paying Lightning invoices from funds that you hold on eCash mints. Now, really, the main thing to consider is what kind of trade-offs you'd like to make. Whereas before, you would have to consider this kind of considerations as well, like how easy it is for me to pay a big Lightning invoice, for example, that would require me to spend from multiple mints at the same time. I hope it was clear. And now the final, yeah, we have time. Great. The final thing I wanted to touch on is channel depletion, which is quite a big topic on Lightning, and I think maybe it's a topic that we can try to have some more hands-on workshops inside the lab as well, maybe a bit later. And so I bring it on today because René Picard, which is someone doing a lot of research on this specific topic, on the topic of channel depletion, pathfinding, Lightning Network topology, things like that. And so he posted on Delving Bitcoin about basically it's a summary of the different mitigations that have been considered so far, that exist in the design space so far, in order to mitigate channel depletion. But before we go to this post on Delving Bitcoin, maybe it's good to have some context on what channel depletion is. So basically, to give some definition, channel depletion is when the large majority of funds inside the channel are on one side of the channel. So for example, here, almost all the funds are owned by the peer on the left, and the peer on the right doesn't have any funds, almost any funds yet left. So basically, you just have the channel reserve that is still there, but you cannot really send funds from the right to the left anymore because there are no funds on the right side of the channel anymore. And so we say it's depleted, more precisely in the context where the channel is often used to go from right to left, of course. Because if you want then to go from left to right, of course, this channel is not depleted for you. and you have on the opposite, you have a lot of funds that you want to send to the other side. But channel depletion typically occurs. Oh, sorry. Thank you. Thank you for telling me. I don't know why, though. Let me just. Thanks for telling me, Alphonse, because I was really talking a lot. Let me. Where is my mouse? Yeah. All right. Okay, should be good now. Yeah. I check out my. Okay, great. Thank you for telling me, Alphonse. So yeah, what I was saying is, so I was explaining with this small drawing what channel depletion is in this context. And so basically, here you have two nodes that share a channel. And so we represent how much funds are on each side. So here you have the funds that are owned by the left side with the color blue, and the funds held by the right, the peer on the right in the color green. And so you can see that the peer on the left has almost all the funds on his side, on their side, and there is almost nothing left on the right side. And so if you want to route a payment through this channel from the right to the left, you won't be able to do so because you need to have funds on this side to be able to push them to the other side. But on the other hand, you can absolutely send funds from left to right. And so we say that a channel is depleted basically when almost all the liquidity of a channel is owned by um, one of the peers, and there is the idea that it's a stable state of the channel. So basically, what this means is that we end up in this situation, and we end up there because the payment flow is uh, uh, almost always from right to left. And so that's why, that's in this case, we say that the channel is depleted. And so for long, one of the so we knew that it was always quite clear that it's something that could happen in the Lightning Network. Um, for example, because we know that there are some nodes that are typically only receiving money. For example, merchants are mostly receiving money. So sometimes they can also send money, for example, to pay their providers. So for example, let's say I have a little shop and I'm buying I don't know vegetables from some local farmer, and I accept Bitcoin Lightning in my shop, and the farmer agrees that I pay for the vegetable um, with Bitcoin Lightning. Then I'm kind of doing both. But a lot of the time, merchants are only receiving and consumers are only sending. And so that's a situation where it was really anticipated since the beginning, basically, that it would lead to channels depleting, because basically the flow of payments is only in one direction. And so that's what we call sources and sinks of liquidity. So a source is someone that always pushes funds away, and a sink is someone that only receives funds. And so for long, it was believed that it was basically one of the primary reasons why we saw a channel depletion. And just to be clear why it's important, is because when a channel is depleted, you cannot use it to receive payments anymore. You cannot use it to send payments anymore, and so basically it's become useless. So it's bad if it's your channel. It's bad because you have a channel that you can't use anymore, and you need to either rebalance the channel or you need to close it. And it's bad for the network because from the network point of view, other nodes that don't have access to distribution of liquidity inside the channel, they don't know that the channel is depleted, at least at first. And so they will attempt to route payments across this channel. And so the payments will fail because the channel is depleted. And so then, after a few attempts, other nodes will learn that the channel isn't reliable because they tried multiple times to route the payments through this channel and it failed every time. And so they will remove this channel from their pathfinding algorithms. But it takes some time to build this this historical data about past payment. And so for some time, you will have failed payments for every time you try to route through this channel. So it's bad for everyone, basically. And so we believe that it was occurring naturally because of sources and sinks, and that, for example, if we had a circular economy where, sorry, here this drawing is basically, here you have on the left, you have a source, and on the right, you have a sink. You see that the payment flows only in one specific direction. And so we believe that if we had a circular economy, so it's a bit like what I described earlier with a merchant that receives but also sends, and everyone is buying stuff from other people with Lightning and selling stuff to other people with Lightning. So really things are balanced out. Then we believe that there wouldn't be channel depletion, but Picard in previous work showed that such depletion still occurs even in perfectly circular economies. And it's due to several things, but basically it's because you have cycles in the graph, and you have also the fees on both sides of channels are not symmetrical. So basically on one direction, it costs you, for example, 100 sats, or let's say it costs you 0.1%. You have a 0.1% fee to go from left to right. But to go from right to left, you have only 0.0001%. So it's really cheaper to go from right to left than to go from left to right. And so this explains why quickly this explains why all other nodes will choose to route, will only use this channel to route from right to left, and never or almost never from left to right. So it's due to both cycles. So it's a bit more complicated to understand really why cycles matter, and to the asymmetry of fees on both sides of channels. And so Picard's the conclusion is that the natural stable state of a Lightning topology, so after a lot of time passes and a lot of payments have occurred, is what we call a spanning tree. So the spanning tree itself is not necessarily always the same tree, but you always have a spanning tree, while all other channels are depleted. And so what is a spanning tree? Basically, it's in your network graph. You have a tree that connects all the nodes together, but it only goes through each edge, so each node once. So if I think I have the Wikipedia page here because you have some visual representation. I hope you can see my screen. Not sure. Let me just check. No, you cannot. I'm just going to stop and share the screen again. Okay, I see what I did wrong. So here, for example, it's a spanning tree for this topology. So if you could see this as some weird Lightning network, where each segment is a channel, and you have every red circle is a node. And so spanning tree in this context is a tree that connects all the nodes together, but going through each node only once. Yeah. And so what this means is that you end up with some kind of hub and spoke model where almost all the channels are depleted. So all the channels are unusable for routing, except a few of them. And so that's what we end up naturally, and we can see it in practice as well. Um, and so you have only a few big highways, if you will, that are still usable after some time, and the rest is depleted. Uh, and so yeah, Picard found that it's a stable state, and so that's why it's important to explore mitigations. And so I have the link about mitigations against channel depletion here. And so basically, it gives a list of two big strategies. So basically, you can either have protocol changes inside Lightning, so you can change the Lightning protocol, or you can have people change how they configure their Lightning node. So the big advantage of the voluntary node behavior change is that you don't need to do a protocol change. But the big disadvantage is that how can you be sure that people will do this at scale? Because usually it requires a lot of people to adopt this new behavior for it to have an effect. And so in protocol changes, so as we can see, one of the big issues with channel depletion is the fact that the rest of the network doesn't know when a channel is depleted that you cannot use it anymore to route payment. They must find out the hard way by trying to send payments, and after a few payments have failed, they will decide to not try to route through this channel anymore. But a great way to reduce the impact of channel depletion on network-wide routing would be to share liquidity information. And so basically right now we have the gossip protocol, which only shares, which only tells the whole network, there is a channel here between this peer and this peer, and the capacity of the channel is, let's say, 1 Bitcoin, but you don't know the liquidity distribution inside the channel. And so one way we could reduce the impact of channel depletion would be to share more data in the gossip protocol in order to share liquidity details. So for example, to know that in this channel, which doesn't belong to me, in this one BTC channel that I'm not a part of, there are 0.1 Bitcoin on one side and 0.9 Bitcoin on the other side. And this way I know that if I'm trying to route 0.2 Bitcoin, it will not be able to go through the channel from the 0.1 side to the 0.9 side because there isn't enough liquidity to route my payments through this channel. And so there are different propositions inside this proposition, different possibilities. One of them is to do some local sharing. So the idea that you already have liquidity details about the channels that you are a part of. So basically, if I am this node here on the top, I know in details how the liquidity is distributed inside this channel and inside this channel because I'm part of both channels. But I don't know what the liquidity is inside this channel here. And so the idea of neighbor of my neighbor or friend of friend network is that we could receive or ask for some information from our peers, from the people we share a channel with, and ask them, do you know, so I see that you have a channel with this peer. Can you tell me if there is enough funds to send a payment of this side? So it could be either a query when we want to make a payment, we want to first check if there is enough liquidity on the right side of the channel to make the payment, or it could be a more proactive mechanism, if you will, where you share details in advance, and this way your neighbors already know the information uh, before they try to return the payment, and they don't need, sorry, to ask for the information. So that's the friend of a friend network proposal. I think I saw, yes, user PRH, uh, who also mentioned a similar solution, which is a query message. So where you can query a peer to ask them uh, about liquidity details in a specific channel. So basically, the idea is to share more information about liquidity distribution inside channels you are not a part of. Uh, and yeah, so it has the pros are that routing becomes much easier, of course, because right now we are trying to route payment across the network, but we don't know everything. It's like if Google Maps were trying to find a route through the city, but didn't know which roads are closed and which roads are open, and you have to try each time to see what is the current state of the road. Here, if we had more sharing of information, it would be easier. But the cons of this proposal are that you cannot know really if a peer is honest, and you increase the bandwidth, so you increase the number of messages that peer exchange, and of course you have a big privacy implications, because if you're able to know to see if you're able to query or to gather information about the liquidity distribution inside a channel, then if you know the liquidity distribution across multiple channels and over time, you can be able to uh, know what when payment occurred and where they went, and so it arms the payment privacy of Lightning. You can have routing coordinators. That's another option. So basically, it's already being tried a bit with trampoline routing. So basically, the idea of trampoline routing is that it's what Async does with Phoenix. And so the idea is that instead of so for example, your Phoenix node trying to compute the route himself, it will um, rely on, in the context of Phoenix, it will rely on Async node to compute the route on behalf of the user. And then the Async node will take care of computing the route. Right now, there aren't, I think, other implementation of trampoline routing, which means that the Async node, when it does this trampoline routing, learns basically the final destination of the payment. But if there were multiple trampoline nodes, the idea of the trampoline routing protocol is that the trampoline node only computes the route up to the next trampoline node in the route, and not necessarily up to the final recipient of the payment. So this consideration helps mitigate a bit the privacy implication of trampoline routing, because else it's really not great for privacy, because the trampoline node sees exactly where you are trying to send money. But it's currently the case with Phoenix and Async, for example. And of course, another problem is that if you are usually relying on a trampoline node or some other kind of coordinator to find routes for your payments, then if this coordinator stops responding to you, either because they have a malfunction or because they are actively censoring transactions, for example, then you're a bit stuck because you don't necessarily have other ways to compute the route for yourself. But it could also be some kind of complementary mechanism. So basically, your node could try to compute the route uh, on itself, and then see what a coordinator has to say, what if it has other routes to suggest, and then you could combine maybe the two routes into a route that has a higher probability of working, things like that. Then you have opportunistic routing, which resembles a lot how the internet traffic, so the internet packets are routed, which is basically uh, best effort forwarding. So in Lightning, what we have is source routing, which is basically you as the sender of the payment, you compute the whole route from you to the recipient. But one more efficient way is to say, uh, I just send the packet, so in the context of Lightning, the payment to the next node, and then the next node now knows where I want the packet to end in the end, so it knows my recipient, and then I let the other node, which has additional information compared to me, I let the other node decide where to forward the payment next, and so on, and so on, and so on. So it's great because each node, when the packet reaches it, is in the optimal position to determine which route is the best at a given point in time. No one in the network knows better than them. But it has huge privacy concerns, of course, because the sender and the receiver are known to everyone that is involved in the routing of the payment. So it's bad in that regard. Um, Symmetric channel fees. So basically, the idea would be to enforce at the protocol level that the fees on one direction, uh, so that the fees on both directions of the channel must be the same. This would help mitigate cases where a channel gets depleted because uh, the fees on one side are really cheaper than on the other side, and so it's only used in one direction and never in the other direction. Um, then you have partial forwarding, but to be honest, I'm not sure to understand what this is. So maybe if someone has an idea. Uh, and multi-party channels, of course, can make things more efficient. But if we talk about multi-party channels, we talk about soft forks if we want to do this efficiently. So it's really, yeah, it's more for the culture, I think, because it's one of the less likely to happen. Um, and then you have behavior adoption by routing nodes, so which doesn't require a Lightning protocol update. You could, for example, have a behavior that is symmetric channel fees. Instead of enforcing this at the protocol level, you could say that it's better for the network, and you could have not necessarily symmetric channel fees, but uh, dynamic pricing. So for example, you update your fees depending on how much liquidity is on your side. Uh, so it's already quite common with either programs like CL Boss or LND Manage that automatically adjust fees depending on the state of the channel. Fee rate cards, which I think are proposal to have an adaptive fee rate depending on the amount. Uh, yeah, no, it's depending on the current channel capacity. So basically, you have the fees are different depending on on the proportion of funds that are on your side of the channel. So basically, it's the same idea is automatically adapting fees, but this time with fee rate cards, you have less updates that are broadcast inside the gossip layer of the Lightning Network, because instead of, like is the case with automated solutions like CL Boss or LND Manage, in which you you send an update message every time you update your fees to reflect a new state, to adapt to a new state of the channel. With fee rate cards, I think the difference is that you just set up your fee rate cards, not necessarily once, but every now and then. And so you say, oh, actually, no, it's not how it works, I think. So you have fee rate cards. Yes, actually, yes, that's I'm not sure how it works, because the idea is basically, instead of updating your channel fees every time you want to adapt the fees, you just publish your rate card, which says that when my capacity is 0.25%, the fee is X. When my capacity is between 26 and 50%, my fee base is Y, and so on. But I don't know how other nodes should be able to know how basically a routing node should pick the rate to pay based on their current guess of the channel's capacity. Okay, interesting. So basically, it's a trade-off between doing a lot of updates on the gossip layer in order to broadcast to other nodes in the network what is your new fee rate, which is basically what things like CLBOSS and LND manage do. And in fee rate cards, instead of doing that, you publish less frequent updates. And so basically you say, when my channel capacity, when I have on my side less than 25% of the channel capacity, I charge this amount. When I have between 26 and 50% of the channel's capacity on my side, I charge that amount, and so on. And nodes that want to route through your channel basically have to guess what is the current fee distribution inside the channel in order to select the appropriate fee when they are computing, when they are building the route. And if they guessed wrong, you just fail the payment, I guess. Or maybe you can have some kind of tolerance threshold. But that means that it's a trade-off, because between update frequency and payment success rate, basically. Okay, interesting. Negative fees, which are basically you can pay people to route your channel. And so in that case, here, for example, if we wanted to unstuck this channel and to reverse its depletion to make it usable again, so basically let me just think to not say something dumb. Yeah, basically this node could start how would it work actually? So if this node charges negative fees, yeah, this node could start to charge negative fees, and which means that when a payment goes, no, it's this node that could charge negative fees in order to incentivize people to move liquidity from there to here. Yeah. So this node on the left could start charging negative fees. And so you would be incentivized to route your payments from here to here when you select a route. And this would opportunistically use the payment of other people that go through this channel to rebalance the channel at the same time. And you have inbound fees, which are basically right now on Lightning only for example, if a payment goes from left to right, only the peer on the left will charge fees and the peer on the right will not. And the reasoning behind that is that only the node on the left is actually providing liquidity that moves during this payment. And the idea of inbound fees is that the other node can also charge fees. And so this enables the other node to have a say in how the liquidity is directed. And so, for example, they could here, for example, in order to avoid depletion in a state where the depletion is not completely achieved, so in a state where the liquidity is a bit more balanced, this node could start increasing their inbound fees in order to discourage users from routing from there to there, in order to at least slow down the rate of depletion of the channel. But of course, it's a bit difficult to uh, to set up, and because when you set your inbound fees, it affects how much your peer is able to route through this channel as well. Um, you have flow and congestion control. I think it's one of the main mitigations used today. Uh, and so basically it's what we call valves or control valves. And we use something called the HTLC maximum MSAT field, which is also something that is an update sent on the gossip layer of the Lightning Network. And so this says to other nodes, this indicates what is the maximum amount per HTLC that you are willing to route through your channel. So for example, if this node, let's say, was to say that their HTLC MSAT amount, HTLC maximum MSAT, is 1 million, they will refuse to route from there to there any HTLC that is bigger than 1 million. And so other nodes that try to send payments across the network, they will compute their routes accordingly to avoid sending HTLCs bigger than the HTLC max value across this channel, because they know that the channel will refuse to process the payment. And so if you have a channel that becomes very depleted, so in this case, for example, here, you can see that once again, any payment attempting to move liquidity from the right to the left will likely fail because there isn't much liquidity left on the right side of the channel. And so what you can do as a node runner is, if you want to, because what will happen if other nodes try to route payments across this channel from right to left is that their payment will fail. And so they will, in their pathfinding algorithm, the reputation of your node, if you will be decreased, and they will stop selecting your node in their routes. But what you can do to avoid that is that when you see that your channel is depleted, you can set the HTLC max amount to a very low value, or even to 0. And this says basically to other nodes of the network, don't try to route payments through this channel, or only for small amounts. And so this way they don't try payments that are that will fail anyway. And so it avoids, it's great for the nodes sending payments because it avoids unnecessary failures. And it's also good for you as a node runner, as a routing node operator, because it means that you, once your channel is back to a more usable state, a more usable liquidity distribution, then you can just update your max amount HTLC value again, and nodes will come again and start routing again through your channel, because since they don't have past failures in their history, they have not flagged your node as an unreliable node. Yeah, that's it. And of course, then you have what René Picard calls the reverse logistics, so which is basically all the kind of off-chain or on-chain rebalancing. So basically, once liquidity is all on one side of the channel and the channel cannot be used anymore, you can rebalance the liquidity either with peer swap, with loop, with splicing, and stuff like that. And so, yeah. And then you have hierarchical topologies, but basically the idea is that we embrace the fact that we will end up with a few channels that are usable in the end, and all the other channels are depleted, and we just accept this, and we have a spanning tree, basically a core node of network, really a highway of channels. But yeah, basically it's not really a solution to me, because it's basically just the same solution as we arrive in the end, without all the build-up. So yeah, and there are some quite interesting. So here is just Bastien Tinturier from A5 saying that they are using the HTLC valves currently in Eclair, which is great. And a comment from Ziman, which I think is quite right, which is that we have to accept that any solution to payment failure requires on-chain action. And so basically, I think, yeah, in most of cases, you have to accept that you will end up with some level of channel depletion, and it requires some on-chain activity, some of on-chain rebalancing, for example, in order to get liquidity back to where it's needed. And so now what we can optimize is this on-chain costs. So for example, there are things like forwardable peer swaps, where you can, with only one on-chain transaction, do some kind of circular rebalancing across multiple channel, and at the same time you settle the rebalancing with one on-chain transaction between two of the nodes. But in the end, you are always, it seems at least, that you will often need to have some on-chain transaction and on-chain cost, and the real design space, it seems to me, actually, at least, would be how we can mitigate and reduce as much as possible these on-chain costs. So yeah, that's it about channel mitigations. I hope it was interesting and it was clear. I think it's really an interesting topic with a lot of research and still a lot quite wide design space and a lot of things to simulate, to a lot of tools to build and things like that. So if you have any ideas, if it's a topic that is interesting to you, feel free to reach out and to tell me. So I have already a few ideas of things that I can propose to you as some side projects and stuff like that that we can take a look at inside the lab. But I'd like to know if it's interesting for you as well, of course. Great. So that's it for today. Thanks a lot for joining us. I see that we stabilized at 10 people, which is great. Thanks a lot for that. We'll stop sharing. Maybe I can just quickly share. I think I closed it actually. What I was saying is I can quickly share the link to the Telegram group again, if in case someone wants to join. I think I saw that a few people joined during today's session. Here you go. Yeah, here you go. Just quickly share screen. Yeah, perfect. Great. So thanks a lot. Thanks, Jean. Thanks, Alphonse. Thanks, Bitcoin Safari. Thanks, Lunez. Thanks, Kauga and Guyenne. Yeah, thank Ka. Yes, that's Ka. Sorry. Thank you. Thanks a lot. I will be starting tomorrow, and so Wednesday and Thursday I will be at the Lightning Summit in Viareggio. If anyone is there, so it's a small technical conference. I don't know if anyone will be there, but if so, feel free to come have a little chat with me. Would be a pleasure. Thanks a lot, everyone. Thanks for everything. I'll keep you posted about some more maybe practical workshops and stuff like that on the Telegram group. So that's why it's important to join. Thanks a lot and see you soon. Bye bye.